In this video, I'll be solving problem 10.5 from Taylor's Classical Mechanics. The problem asks, a uniform solid hemisphere of radius r has its flat base in the xy plane with its center at the origin, as I've drawn. Use the result of problem 10.4 to find the center of mass. And the result of problem 10.4 is right at the top. It's simply expressing the integral of a function of the position vector over a volume in spherical coordinates. We'll start by remembering that the center of mass position, r, is equal to 1 over the mass times the sum of every individual bit of mass times the position of the individual bit of mass, which we can translate it into an integral by integrating over a volume r dm. And because this is a uniform hemisphere, we know that dm equals rho dv, where rho is the density, which is mass over volume, which is equal to mass over 2/3 pi r cubed, because it's half a sphere. So we'll continue here. Then we have r equals 1 over m times the integral over volume of rho r vector dv. Now, let's break this down and do it in each individual coordinate separately. We can see by symmetry that the center of mass in x and in y is going to be 0 because the hemisphere is centered at the origin. So we'll only do it in z. Then we will also have to remember, since we'll be doing this in spherical coordinates, that z is equal to r cosine theta, where theta is the angle measured downward from the z-axis. So with that, we're ready to integrate. Z will be, let's pull the r out, the rho, sorry. Z will be equal to rho over m times the integral over volume of z dv, which is r cosine theta dv. Now we'll use the result of 10.4 to put that in spherical coordinates. So it'll be rho over m integral of r squared dr sine theta d theta d phi, and then the function is just z, r cosine theta. Our limits of integration here will be in phi, which is in the xy plane, all the way around from 0 to 2 pi. In theta, remember measuring down from the z-axis, we'll be integrating from 0 to pi over 2. And in r, we'll be, of course, integrating from 0 to capital R, the radius of the hemisphere. So let's start by pulling out the phi integral. There is no function of phi, so it'll just be the constant 2 pi. Let's move all the r's together. So then we'll have 0 to r, r cubed dr, and then 0 to pi over 2 we'll have sine theta cosine theta d theta. Now we can solve this with substitution. So if we let u equal sine theta, then du will equal cosine theta d theta, which is exactly what we have here. And then the integral of u du will simply be u squared over 2 equals sine squared theta over 2. Z will equal rho over m, 2 pi, 0 to r cubed dr, and then we'll have sine squared theta over 2 from 0 to pi over 2. Sine of 0 is 0, obviously. Sorry, just writing this all over again. Okay, we'll bring down the 2, and then sine of pi over 2 is 1, so sine squared of pi over 2 will also be 1. And then sine of 0 is 0, so 1 minus 0 is 1. We multiply the whole integral by 1, and there it is. So we'll do the next integral here. So we've got 2 pi over 2m. We'll cancel those in a second, and we're integrating r cubed dr from 0 to r. That'll give us capital R to the 4th over 4. So our end result for the center of mass in Z is, let's plug in our actual value for rho, which is m over 2/3 pi r cubed. So we'll have m over 2/3 pi r cubed times 2 pi over m r to the 4th over 4. Forgot a 2 in here. So then we cancel, and we are left with 3/8 r, which is a reasonable place for the center of mass to be.